Okay, so thank you all for coming, and thanks for that great introduction, Jess. I'm Claire Puleio. I'm a PhD student here at the University of Alaska Fairbanks. And today I'm going to talk to you guys about some work that I've been doing on Mount Edgecumbe, exploring a reawakened volcano. And this is a very collaborative effort that I've been working on with colleagues from UAF, as well as from the Alaska Volcano Observatory, from the US Geological Survey, as well as colleagues in Spain and Italy. And not to mention Rod, who was there as well, and JR, who I believe is here too, who were photographing and helping document this, which was wonderful. And you'll see some of their photos and work in here as well. Okay, so just a little bit of a background, although Jess kind of went over this already, so I'll briefly just remind you all. I'm a PhD student here, but I got my Bachelor of Science in Geology from Union College, and that's in upstate New York. One of those small schools, but with a great geology program, and that's where I really started kind of getting into the love of rocks. And that's where I took my first volcanology class and realized that volcanoes were actually pretty cool, something that I've thought, my whole life, but really started getting into it in college. Then I moved out to Washington, and that's where I got my Master of Science in Geology. And there I was looking at spatter deposits, which you think of a typical Hawaiian-style volcano with that lava kind of spattering out in those kind of fountains. I was studying how those little pieces of lava, when they land on the ground and pile on each other, how they cool, which may seem very specific, but I found it quite interesting. And then I moved up here in the fall of 2021 to start my PhD in geosciences here. There we go. Okay, so just a little bit of a background as to why I came up here to study volcanoes is we've got a lot of volcanoes in Alaska. So this is, this is from the Alaska Volcano Observatory's website, and you can see all these triangles represents a volcano in Alaska. So we have a lot of them. And kind of that was the main draw of where better to study volcanoes than a place like this where you can explore them in your own state. And you can see along the Aleutian Islands, there's a whole lot of volcanoes there. But I'm most interested in a volcano right down in the corner of this page, which I'll show you with my little mouse here. It's kind of off on its own, and that's Mount Edgecumbe. So Mount Edgecumbe is in southeast Alaska and has shown some signs of recent unrest. For a long time it wasn't doing anything, and now it's showing some interesting stuff going on. Mount Edgecumbe is located down by Sitka, so you can see in the right-hand image there, Sitka's right over on the right, and then across the Sitka Sound is Kruzof Island. And Mount Edgecumbe is kind of right in the middle there, that very classic-looking cone volcano you can see from above. And one thing you might also notice on Kruzof Island is, I'll point with my mouse here, a bunch of smaller little dots and cones and features. And those are all volcanic features as well. So we like to refer to this as the Mount Edgecumbe volcanic field because there's a lot going on. It's not just Mount Edgecumbe itself, although that's the most prominent feature. So Mount Edgecumbe, as I was saying, hasn't erupted, hasn't been doing anything in a long time. According to Tlingit oral history, Mount Edgecumbe may have had some small eruptions as recently as 800 years ago. And then prior to that, there were a number of small eruptions between 6,000 and 4,000 years ago, and then some larger eruptions between 13,000 and 14,500 years ago. So a long time ago. Stuff hasn't been happening lately. Unless you count the April 1st, 1974 eruption at Mount Edgecumbe, where you can see a nice little plume coming out, which in fact was an April Fool's joke and just a bunch of burning tires, so you can see. However, on a more serious note, there are some hazards that are really important to consider when looking at Mount Edgecumbe and its proximity to Sitka. Those larger eruptions that I was talking about 13,000 to 14,500 years ago, deposited a whole lot of ash on Sitka. So here are some images showing some outcrops right in and around the city of Sitka with some really large ash beds. So that's all volcanic ash that you can see in those images. And in Sitka, that's about 3 feet thick. And on Kruzof itself, it's about 100 feet thick. So it's a lot of ash, and that could cause a lot of damage. It's important to note, though, that those 3-foot thick packages of ash were an accumulation of about 20 different events. So it wasn't like Sitka was getting 3 feet of ash dumped on it in one go. It was in these smaller eruptive events. However, some of the packages of ash for each of those events were still very significant and could cause a lot of damage in Sitka and to people who are on cruise off themselves. And there are other hazards associated with Mount Edgecumbe as well, other than ashfall. On Mount Edgecumbe itself, you can get things like lava flows, lahars, which are these like muddy rock flow, muddy ash and water flows, as well as pyroclastic density currents, and those are going to be these hot, ashy rock kind of avalanches, if you will. Not great things to experience. And so those are things that could be on Cruise Off Island itself, and while there's nobody who's living permanently on Cruise Off, there's a lot of recreation that's done there. People are out there hiking, hunting. There's a number of recreational cabins out there as well. So people are out there, and then there are also those hazards that could reach Sitka as well. So important to keep our eyes on this. However, no one was really keeping their eyes on it until April of 2022, and that's when I started getting interested in Edgecumbe as well. So on April 11th, 2022, there was a 2.1 magnitude earthquake centered right around Mount Edgecumbe, and you can see in the blue dot on that left image there where the epicenter of that earthquake was. And this was strong enough to be felt in Sitka. So people in Sitka felt this earthquake, and they looked up the epicenter on the Alaska Earthquake Center's website, and were like, well, that's strange, that's right on the volcano. What does that mean? And so they contacted some folks at the Alaska Volcano Observatory and said, what's up with this? Does that have to do with the volcano? Should we be concerned about this? And so folks at the Volcano Observatory were like, well, let's take a closer look at what's going on over there. And when they looked at the seismic data, which you can see on the right here, and this is data from the Earthquake Center, there was an earthquake swarm going on. So there's a whole lot of earthquakes happening right around Mount Edgecumbe. And that was pretty alarming for a volcano that wasn't really doing anything, and now all of a sudden is having this earthquake swarm. So everyone kind of started to put their eyes on Edgecumbe and to think, well, was there anything happening before that we weren't picking up on because we weren't looking at this volcano? It wasn't doing anything. What was happening prior to this earthquake swarm in April? So folks started to take a look at deformation and seismicity happening on Cruise Off Island. Namely, Ronnie Grappentine, who's at University of Alaska and the Geophysical Institute, him and other colleagues started to look at, is this volcano deforming? So if you take a look at this center plot right here, or the left-hand side plot, your red represents inflation. So what he and others found was that Edgecumbe is actually inflating. It is rising up, kind of imagining almost like a balloon. It's rising up. And in that bottom plot in the bottom right-hand corner, you can see that it's actually inflating at a rate of about 3.9 inches per year. And that's a lot for a volcano we didn't think was doing anything. So they also decided to take a look at, all right, what about earthquakes? Were there any earthquakes happening prior to that April swarm? And that's so you can see up in this upper left-hand corner image, that's plotting out all the different epicenters and locations of those earthquakes. And then down below, that's plotting those versus time. And what they found was that earthquakes started happening there around 2018. And then if you look at that deformation, the deformation started happening around 2018. So around 2018, we started getting all this activity. What was going on there? So what Ronnie Grappentine and his team did was they looked and were trying to model this system, see what would cause inflation like that. And what they found is that I think there's two magma reservoirs beneath Mount Edgecumbe, one that's about 12 miles deep and one that's about 6 miles deep. They think that magma is moving between the deeper one up to the shallower one. So we've got magma movement at depth. Now, that happens sometimes with volcanoes. It doesn't always mean they're going to erupt, but it does mean we want to keep a closer eye on it. And we want to start looking at other things that might be going on the volcano. Is there anything else out of the ordinary happening? And that's when we started hearing more about some local observations of unusual bubbling and maybe some gases on the island. Namely, what we've come to call the bubbling pond. This was an area that was first noticed by Don Cluting, who's a Sitkan, who was over there hiking, and he found this pond that's right on the shore, but it's not interacting with the ocean. It's still separate from the ocean itself, but close to the shoreline, where there was this very persistent bubbling. And that's kind of strange. So he contacted the Volcano Observatory as well, and he took a video and sent it over and was like, is this related to the volcano? You're like, well, I don't know, maybe. And then another report we got was from Shoals Point. So that's in that southeast corner of Cruise Off, where Kyle Ferguson, another Sitkin, was hiking there, and he observed this hole in the ground that had this warm, sulfur-smelling air whooshing out of it. And he was wondering, is that related to the volcano? So the deformation, the earthquakes, strange bubbling, maybe some gas coming out, all of this led me to wonder, are there any additional surface expressions of magma below Mount Edgecumbe? So we do have one surface expression, right? We have this inflation that we're seeing. But is there anything else that's telling us about magma, this magma movement at depth, down deep? And we can figure that out in a few different ways. So namely, we can look at heat and gas emissions from Mount Edgecumbe. So is there any heat or gas on top of this volcano that can tell us about what's going on below the surface? And we can look at this through satellite observations of elevated surface temperatures, through measurements of volcanic gas compositions and the gas flux. And flux is the rate at which that gas is leaving the ground. And we were able to accomplish this by taking 2 field trips to Cruise Off Island this past summer to investigate further. Okay, or back up before we go further. This is a bit of background, just to kind of set the scene for you to know what's going on, why are we interested in Edgecumbe. Now I'm gonna walk you through kind of what we did on the thermal front, and then walk you through what we did on the gas front, and then we'll get to conclusions. So, just so you know what's coming at you. All right, now getting into the thermal. Volcanoes have hot features that can be observed from space. So there are a few things that can be observed from space, right? If you have a lava flow on the side of your volcano, you can see that through your satellite data. If you've got a lava dome maybe coming out of the top, you can see that as well. And you can see things like fumaroles, where you have hot gases coming out of the volcano. But Mount Edgecumbe is not actively erupting right now, so we don't have any lava flows, we don't have any lava domes, we don't have any fumaroles. But there is something else we might be able to still see, even though it's not erupting. And that's these low temperature thermal anomalies. So what are low temperature thermal anomalies? These are these subtle, large-scale, long-term temperature anomalies that have been reported at several volcanoes in the years leading up to an eruption. So sometimes these thermal anomalies will increase before an eruption happens. For example, let's look at Redoubt. Redoubt is a volcano in South Central Alaska that you might be familiar with. On the x-axis of this graph here, we've got time, and on our y-axis, that's our thermal anomaly. And we can see that thermal anomaly increase right up before the 2009 eruption at Redoubt, denoted by that black line. Okay, so do we see those low temperature thermal anomalies at Edgecumbe? And how do we figure that out? So in order to actually figure out if we have these low temperature thermal anomalies, we use temperature data collected with MODIS instruments on board NASA's Terra and Aqua satellites. And what we actually do with that data is we pick a spot on Mount Edgecumbe to analyze, or in our region. Here we're looking at Cruise Off. So let's say we take that red square in the center of that left-hand image there. We look at that red square and we figure out what the median temperature is in that small region. And then we compare that median temperature to some background, and that's that blue area behind, to say, how does this look compared to our background? And that background is an area far enough away from the volcano that it shouldn't be affected by volcanic activity at our volcano. And then what we do is we track how the temperature in our red square changes over time from 2002 to 2021. Okay. Then we perform that same analysis at a whole bunch of areas on our volcano, in the region we want to explore further. So in the right-hand image, that's all of those little blue dots. So we perform that same analysis at every single one of these regions. What that allows us to do is look at how the temperature is changing on our volcano in both time and space. Okay, so what does that actually look like at Mount Edgecumbe? All right, I'm going to show you a video that shows you how that temperature is changing, but let's look at this first. This is what it's going to look like. So you've got Cruise Off Island here. I'm giving you a little bit of scale to orient yourselves. And then Mount Edgecumbe is in the red box in the center. And our colors tell us how the temperature is changing. So we've got a temperature decrease of 1.5 degrees, those are those blue colors, and a temperature increase of 1.5 degrees, those are those red colors. So we're only looking at a temperature change of about 3 degrees. Very subtle temperature changes here. Okay, so let's watch this video and see what patterns we see. It's playing, yay. Okay, so you start to look at this. You see some increases in temperature in some location. Remember, we're starting at 2002 and headed towards 2021. So now we're in about 2006 here. So start to look at this, see what patterns you might notice. Is there any spots that look like they are consistently heating or cooling down, or is it pretty variable? And remember, when we were talking before, the inflation and that seismicity, those earthquakes increasing, began around 2018. So that's a time period we're going to focus in on as we start getting closer to 2018. Do we see any temperature changes that coincide with that increase in our deformation and the increase in our earthquakes as well? And a couple of things to note too about this is you can sort of ignore the water for now. So focus on the color changes on the land. All right, so now we're moving into 2015, and now we want to start thinking, okay, we're just a few years before we started seeing that those changes with the deformation and the earthquakes. Do we start to see any changes here now? So let's take a look and see if we notice any patterns. Now we're in 2018, 2019, and maybe it's pausing. Okay, no, we're good. Okay. All right. And there we go. So there was a lot of changes happening. Kind of hard to tell from that video. It gives you a good idea of what this might look like, but sometimes it's hard to pull data out of that, what we're even looking at. So let's break this down a little bit. I've pulled some screen grabs from that video every 2 years, starting in 2005 and going to 2021, and these are all in June of those years, so halfway through the year. We're marching through time from left to right across the top and then down. So, do we notice anything? So this is what I notice. I noticed some heating that was consistent in kind of that southeast and the northwest areas of Cruise-Off that seemed to return. But if you remember from the video, sometimes we had some heating happening, and then it kind of went away in between this 2-year-long period in between these frames that we're looking at. So I saw it come back a few times, and I was like, that's an area I kind of want to keep my eye on, but it was nothing really consistent. It was kind of patchy. You might look at this and say, I don't think that there's heating in the northwest or the southeast and the northwest corners. It's a little bit hard to tell, and it's not super consistent. And other volcanoes that we've run this analysis for, sometimes before an eruption, we see some really concentrated red colors right around our volcano that totally increase, and it's very clear what's going on. Sometimes it even looks a little bit like a bullseye. We're definitely not seeing that here. But we do see some interesting data. However, in order to interpret this and try to figure out, is this even anything? Is it anything to do with the volcano? We need to look at some other types of data, some other things that we can observe and compare with this. And that's namely gas. So now moving into kind of the gas portion of this talk here. Gas is important because changes in gas emissions at volcanoes are often one of the earliest signs of volcanic unrest. There are a lot of different gases that we can see at volcanoes. So let's take a look at an active volcano here and what gas we might see. We're looking at the surface, right? Because we're looking for those surface expressions of gases. We can get diffuse carbon dioxide that's made its way, either permeating up through the surface, maybe through some cracks or some faults, made its way up to the surface. So we can see carbon dioxide. In a volcanic plume, high temperature gas plume, we can see things like water, carbon dioxide, sulfur dioxide. We can also see similar gases coming out of fumaroles or hot springs. However, Edgecumbe's not an active volcano, right? It's not erupting. So what would we expect to see there? Let's take a look at a dormant, restless volcano and what gases we might expect to see there. We can see a lot of the same gases, they just might look a little different. We're not going to have a big active plume. At the surface, where there's maybe some faulting or some cracks or even just gases permeating through, we can see some diffuse carbon dioxide or hydrogen sulfate. And then we can also get some gases coming up from our magma chamber deep there, some carbon dioxide, sulfur dioxide, that's interacting with your hydrothermal system, and that can also make its way to the surface. So we can see gases at a volcano if we classify it as active or if we classify it as dormant or a restless volcano. Okay, but if we can see them, so what? What can we actually learn from those gases? What do they tell us? So the composition of the gas tells us about the source of the gas. So, is it from the volcano or is it not from the volcano? That's going to be key. And the flux of that gas tells us, remember, flux is the rate at which the gas is coming out of the ground. That's going to tell us about the abundance of that gas source. So how much are we actually dealing with? Okay, so how do we actually determine the gas composition and the gas flux? We can do that in a number of different ways. So we can look at diffuse carbon dioxide, and that's going to be how we measure the flux of that carbon dioxide coming out of the surface. And we determine that through something called an accumulation chamber. Then we can also, in this middle panel here, we can take some direct gas sampling, and then we can analyze that gas, figure out the composition of the gases coming out of the surface. Another thing that we can do is use a multigas to measure the composition of gases in the air. So these are the ways that we look at gas composition and gas fluxes at volcanoes, some of the ways. All right, so let's look at measuring that diffuse carbon dioxide at Mount Edgecumbe. All right, so that was that accumulation chamber I was telling you about. So the accumulation chamber is kind of like a kitchen pot, you can imagine. Stick your kitchen pot upside down, you stick that on the ground, and then the carbon dioxide that's diffusely coming out of the surface is gonna enter your pot. Then it's gonna go up through that tubing into the little yellow backpack that I'm wearing in that picture. And inside that yellow backpack, that green box is a Lycor gas analyzer. And it tells us how much carbon dioxide we have entering our pot. Now, at a very active volcano, oftentimes there can be a lot of carbon dioxide diffusely escaping from the ground. So you take your measurement, you measure what's our flux? It's through the roof, it's huge. Okay, that's coming from our volcano. Other times, it's not as obvious and it can be a little bit subtle. Sometimes we have really low levels of carbon dioxide coming from our volcano. Sometimes it's so low that it's hard to tell, is it coming from the volcano or is it coming from other processes that produce carbon dioxide, like some biologic processes that I'll get into later. So before we did our large trip to Edgecumbe to measure all these gases, we wanted to know how much are we expecting? Are we expecting a lot or expecting a little? And that'll help us plan. So in the summer of 2022, I traveled to cruise off just to get the lay of the land and see how much gas we have. And it turns out, not very much gas at all. Very subtle, not very much diffuse carbon dioxide coming out of the ground on Cruise Off Island. So that would make it tricky. How we can measure the flux of this gas, see how abundant it is, but it might not be from the volcano at all. What if it's just from biologic processes, things like plants and animals making this? What we can do is get the composition of that gas, right? And that composition of the gas will tell us about the source of the gas. So we need to collect samples. We need to collect samples to do a carbon isotope analysis. All right, briefly, we're gonna go over isotopes. So isotopes, if we're looking at a given element, so for example here, we're looking at helium, they have the same number of electrons and protons, but different number of neutrons. The important thing to know about isotopes here is that different sources of these elements, so if we're looking at carbon, if we're looking at helium, maybe we're looking at neon, different sources have different known ratios of those isotopes to each other. So if we're looking, let's say, helium, the ratio of our helium-3 isotope to our helium-4 isotope, it's known what that would be if we have, let's say, a source from the volcano. Okay, so the important thing to know is that when we get our samples, we analyze them. If we can look at the ratio of these isotopes, it can tell us, okay, is that from the volcano? Is it from plants? Is it from certain types of rocks? That's kind of the most that we need to keep in mind here. And these isotopes are going to be key for the data that we're going to analyze later in this. Okay, so back to Edgecumbe. Now we know we need to collect samples and we need to do a carbon isotope analysis because we don't know if this is related to the volcano at all. Now, when we planned to go to Edgecumbe, we chose a number of different sites we wanted to do this diffuse carbon dioxide measurement at. And these sites, which you can see in the right-hand panel here, in both red and blue, were chosen based on that thermal map I showed you earlier. We're kind of targeting that southeast portion and the northwest portion there, as well as Edgecumbe itself, and then Crater Ridge volcanic feature just north of Edgecumbe. Targeted based on that thermal map, the accessibility of these sites that we wanted to get to, and then those local reports of those observed bubbling, which are in blue. We ended up taking about 550 diffuse carbon dioxide measurements using our accumulation chamber, and then we collected about 200 samples for a carbon isotope analysis, so we could see, is this even the volcano? Now let's look at those results. I'm going to walk us through this figure because there's kind of a lot going on here. But like I was saying before, the ratio of our different isotopes that we have is going to tell us about the source. So if you look at our y-axis here, I'm going to use my mouse, this is the carbon isotope ratio, if you will. Now, our sedimentary organics, think things like coal, would plot way down here. That's in our blue. Now, our marine and non-marine organisms, things like plants or small animals producing carbon dioxide, would plot in the pink, kind of right over in this zone. Our freshwater carbonates, think rocks like limestone, those also can give off CO2. Those would plot in this yellow zone here. Our marine carbonates, also rocks like limestone, but in the ocean, those would plot right here in this green zone. But what we're looking for is the mantle. That's our volcanic source. So if it's from the volcano, we would expect the carbon isotopes to plot right around here, okay? So we collected a whole number of samples, all of those dots you can see here. We've plotted them up here, again, with those carbon isotopes on your y-axis, and your x-axis is the concentration of carbon dioxide we have in our samples. So how much did we actually get? What we expect to see is a mixture between air, we're sampling some air, and one of these sources. So is it a mixture between air and those sedimentary organics, or is it a mixture between air and maybe that volcanic source? Now, if it's a mixture between air and the volcanic source, we would expect it to plot, we'd expect all these little dots to plot along this line here somewhere. If it's a mixture between air and one of those biologic sources, like let's say sedimentary organics or those marine and non-marine organisms, we could expect them to maybe plot on this lower line right here. And if it's one of these ones in between, you can imagine a different line showing those different end members, if it's maybe a freshwater carbonate or maybe a lighter marine and non-marine organism carbon isotope. Main takeaway from this is a lot of our samples plot kind of down in this zone here, and they plot pretty similarly to if they were going to plot on one of these biologic lines. And our takeaway from this is likely the source of the diffuse carbon dioxide that we were measuring all along the ground, all over the surface of Kruzof, is largely a biologic source and likely not from the volcano. But there's still more to explore at Kruzof, namely that bubbling pond. This is what Don Kluding observed on Kruzof Island. And this was noticed a few years ago. So during our first trip in June, we wanted to find this pond, and we wanted to find this bubbling, and we wanted to sample it. And we found the pond, and the first day we went there, it was bubbling. We were all very excited, and we took some samples. We weren't able to do kind of the extensive analysis that we wanted to do, but we saw some bubbling, take a few measurements. We're like, we'll return tomorrow, and we'll take all the samples that we want. But then it wasn't bubbling tomorrow. And then we returned every day afterwards, and it wasn't bubbling. We'd always check, and we'd stop by, see if it was bubbling, never bubbling again. So we're like, okay, well, was it a crazy coincidence that a few years ago, Don saw this very consistent bubbling, and then we just happened to see it one day, and then it wasn't there ever again? Or is there some sort of pattern to this bubbling, and we just happened to miss it? And the first day when we were there and we saw the bubbling, it was at a very high tide. So we're like, well, maybe it's related to the tides, right? This pond is close to the ocean, right? The water in the pond is not interacting with ocean water. However, it's close. So maybe at high tide, you get an overpressure from all that water coming in, and so that pressure is kind of pushing down on the surface and allowing for that gas down below to release. It wants to go into the air where there was a lower pressure. Perhaps that's what's going on. So when we returned in August, we installed a number of trail cameras around this pond, set them to time-lapse to see, are we gonna capture this bubbling? And a few days later, we went and we grabbed the footage, combed through it to see, do we see the bubbling? Are our cameras even good enough to be able to pick up on bubbling in a pond? And they were. So this is an image from one of our trail cameras. Beautiful, looking out towards Sitka. It's a very beautiful area. And right in that red circle, that's the bubbling. We're very happy we found the bubbling. And indeed, it was happening at high tide. So we noticed that the bubbling would start about 40 minutes before high tide and end about 50 minutes after high tide. But it wasn't every high tide. It was only the highest of the high tides. We seem to think it was only happening when the tides were above an 8-foot tide, maybe. And this made it quite logistically difficult to find a time when it was going to be those highest of the high tides above that 8-foot tide, and it would be daylight, and it would be within the hours that we were allowed to fly in the helicopter, and so it was really tricky to line up this time, but we had kind of one shot. We lined it up. We're like, there's this one day we can go on our final day, and if we're right, it'll be bubbling. And it was bubbling. We were very excited. So this is what that bubbling actually looks like. And you can see it right here. It's quite persistent. It's pretty vigorous bubbling, and it would be that persistent and consistent the entire time, you know, the 40 minutes before high tide and 50 minutes after high tide. And you can also see there are some smaller areas kind of up in the front here where there's some smaller bubbling, and that was more sporadic. It wasn't very consistent, but it was there. And sometimes you can see in the back here, it's a little harder to see, there would be another very persistent bubbling area. So the day we went, we had these kind of 2 persistent bubbling areas that we were able to sample to our heart's delight, and we did. And so we collected 20 samples here to analyze the gas composition and to look again at those carbon isotopes, and this time helium isotopes as well. It would help us try to get a better understanding of the composition of that gas, which would tell us about the source of the gas and if it is even from the volcano at all. So let's take a look at those carbon isotopes again. So we're back to the same figure. We're on the y-axis, we're looking at our carbon isotopes, and we're looking at those different sources that would produce the CO2, the carbon dioxide. On the x-axis, we have the composition, or the concentration of our carbon dioxide. And so these samples plot a little bit differently than the ones we were looking at before. These are the ones from the bubbling pond, and those are shown in blue there. You can see right here. And so it's a little different. They seem to be, again, this lower line here would be if we were between air and this, maybe a biologic source down here. And this upper line is if we're mixing between air and that mantle source. And it seems to maybe be pulling up and off of that biologic line closer and closer to that mantle source. And the tricky thing about these isotopes, or about the carbon isotopes, is we can be mixing sources. So maybe we have a volcanic source in there, and then we also have a biologic source in there, and it's mixing somewhere. Maybe we have some marine carbonates in there, some of that limestone. It makes it really tricky to pick out and see, is it from the volcano? Is it a weird mixture of a biologic source and something else? But these were indicating it's mixing with something. Something interesting is going on here. It's not your kind of typical biologic source, and there's the potential it's mixing with a mantle source, that volcanic source. Or there's a potential maybe it's mixing with some crustal carbonates, which are those limestones. And from these results alone, we can't tell that. So this won't help us narrow it down, but we need a little bit more data to be able to really get at the composition and the source of the source of this gas. So we can look at the bulk chemistry of the gas. We can see what is this made up of as a whole. Now, this plot shows you, kind of breaks down all the different components of this gas. And we find that it's mostly nitrogen. It's about 96.6% nitrogen, which is very high. And oftentimes when you have a sample that has such high nitrogen, we think we just sampled the air. Air has a lot of nitrogen in it, right? So if we sampled air, we would also expect to see pretty high levels of oxygen as well. Got a lot of oxygen in the air too. Not as much as nitrogen, but we would expect to see higher levels of oxygen. And you can see in this sample over on the right-hand side in that gray bar, we have about 0.3% oxygen. Not a lot of oxygen. So that tells us we didn't just sample air. This is a good sample. It's just a weird sample. Other things of note in this sample are that we have some very low CO2, carbon dioxide. We have about 1.7% carbon dioxide. And then we have a entirely lack of hydrogen sulfate. So overall, our bulk chemistry says no clear volcanic signature, but you can't quite rule it out yet. So that brings us to, okay, what other data streams can we look at? What else can we look at to try and help us really narrow this down and see if it's actually from the volcano? We can look at helium. Okay, so helium on our y-axis here, it's R over Ra. What that really means is we're looking at our ratio between our helium-3 isotope and our helium-4 isotope compared to a standard of air. But think of our y-axis as being our helium-3 versus helium-4 isotope. And then on our x-axis, we're looking at our helium-4 isotope with our neon-20 isotope. Now, all that's to say is on a figure like this, if it's from the mantle, if it's that volcanic source, it should plot up in this right-hand corner. Oop, if I can get my mouse to cooperate. Okay. It would plot here. If it's from the crust, it would plot way down here in the lower right. And if it's air, it would plot right here. Now, our bubbling pond sample is that black dot, and it plots like right on air. So, once again, no clear volcanic signature from helium. And that's kind of exhausted sort of everything that, with the samples that we have, everything that we could kind of look at, trying to figure out what that source of the bubbling pond is. So in the end, no clear volcanic signature, and it might not even be from the volcano at all. Which brings us to start to think about what other mechanisms that could produce that strange bubbling. Why else would we maybe get bubbling in a pond that was so consistent? That's another rabbit hole to go down that gets more into the biology realm, which I'll probably go down that road, even though my advisor might not want me to spend that much time going down that road, but I'll be curious. Okay, so what else did we look at? We did a gas flight. So we did a gas flight so that we could measure the composition of the gas in the air over the volcano. Is there anything coming out of the volcano into the air? And we do this using a multigas, which is a multiple component gas analyzer system. And this will tell us, this can measure water, carbon dioxide, sulfur dioxide, and hydrogen sulfate in the air. And what we did was you get in a helicopter, you stick this multigas with a little tube going out the window so you can sample the air, and then you fly tracks going up the flanks of the volcano and then down into the crater of the volcano and measure what that air is. And what we found was no gas is detected above atmospheric background. So it's just the atmosphere, nothing interesting going on. We had our carbon dioxide levels are consistent with what you would expect to be in the air, and then we didn't see any sulfur dioxide or any hydrogen sulfate, those other volcanic gases. And what about that hole at Shoals Point? This is where Kyle Ferguson was hiking down there and found that strange-looking hole. And we wanted to go find that hole and sample it as well, because he said there was that warm, sulfur-smelling air wishing out of it. We wanted to measure the gas and see, is that from the volcano? Something strange is going on. And we were able to find this hole, which kind of felt a little bit like a miracle, because along the beaches is all these beautiful old lava flows and all these cracks and little holes, and can be kind of tricky to walk all over. But it'd be really hard to find a little hole that someone said, hey, there's a hole out there somewhere, and you go find it. And Kyle gave us wonderful directions, and we found it very quickly. It's kind of funny. So we found this hole. We stuck our multigas over it, measured the air, and again found that there was no elevated carbon dioxide, hydrogen sulfate, or sulfur dioxide. So we weren't seeing those volcanic gases. And what we think it was just a little bit of a lava tube from a pocket. You kind of, you couldn't really see down in there, but if you're creative and you take a little headlamp and your phone and you, with a lot of trust in your grip, stick your arm down there and twist it around, and you can get a video and you can see that it looks like it's just a bit of a lava tube, and maybe there was some air kind of getting trapped up into it and interesting pressure systems happening so that the air was kind of whooshing out of it when Kyle was there. Okay, so let's summarize everything we did at Edgecumbe here. We found that there are subtle temperature changes all over Kruzof Island, but it's unclear if they are actually related to the volcano. We took our diffuse carbon dioxide measurements all over the island, and you can see on the right-hand side, again, that's showing you all of those sample locations and measurement locations that we went. And we found that most of that gas seemed to be largely biologic in origin. The gas that we measured from the bubbling pond showed no clear volcanic signal. There was no volcanic gas detected during the gas flight, and there was no volcanic gas detected at that hole in Shoals Point. So what does this actually mean for Edgecumbe? There's no overwhelming thermal or gas volcanic signals at the surface. However, if we go back to the beginning there, Ronnie Grappentine's work with him and other colleagues, the idea that there's two magma reservoirs beneath Edgecumbe, one at 12 miles deep, one at 6 miles deep. Perhaps all the volcanic activity that's happening at Mount Edgecumbe may just be constrained to those magma reservoirs. Maybe there's no gas permeating outside of the reservoirs. We're not seeing any interaction with those gases being able to escape to the surface. It could just be confined to just in those reservoirs, and they're staying put for now. But the most important thing that this work does is establish a very good background for Edgecumbe that we can measure against in the future. So now we know, what is Edgecumbe's background? What is it normally doing? And then if those things change, that's when we know we need to keep a really close eye on Edgecumbe. Because oftentimes before a volcano erupts, we see changes in our gas emissions, right? Sometimes those are the first indicators of volcanic unrest, is changes in gas emissions. We might see changes in that rate of inflation. We might see an increased number of earthquakes, magnitude of those earthquakes, or the location of those earthquakes. But we would expect to see a change happen. So now we've been able to establish that good background to measure that change against. And oftentimes in Alaska too, we might have some volcanoes that always have a lot of earthquakes. That's just how they normally are, and that's not really a cause for concern. That's just what that volcano does. Sometimes we have volcanoes that are off-gassing a lot, and that's just kind of what it does. Not really a cause for concern unless we see that change in behavior. So now we know what to measure that change in behavior against at Mount Edgecumbe. And we would definitely expect to see that change happen if an eruption was imminent. And we hope that no eruption is imminent, whether it be a true eruption or an April Fool's joke. All right, thank you very much.
My question is, how did you guys determine that the magma chambers were at 6 and 12 nautical miles below it?
Yeah, that's a great question. So this is an area of geodesy that other people in the room would probably be able to speak to better than me. But what you can do is look at the rate that the volcano is deforming at and kind of the shapes that it's making, how it's moving. And you apply kind of an inversion, but basically what you do is look at what could be causing that change in shape on the surface. So what sort of, you would expect to see some change below surface, right? Maybe some inflation really deep happening. Maybe you've got a magma reservoir that's growing, right? And that would, because you see that change below ground at the surface, you're also gonna see a change in ground. It's just gonna look a little bit different because it's a lot further away and over a larger area, right? So what you can do is take that change that you see on the surface and kind of back calculate to see what small change in shape would you see below surface, where would you see it, what size would it be, how would it be growing and moving, would it be an oval, like sometimes we like to think magma chambers as being, would it be like a long oval? And so it's a lot of back calculating based on what you see at the surface to see what would be able to cause that.
Any other questions?
How did you calibrate your multi-gas instrument to make sure that it was actually picking up what was there or not picking up gas?
That is a good question. I myself actually didn't perform the calibration on the multi-gas as my colleague Laura Clore, but you use calibration gases. So you take known gases that you can purchase. And you're like, okay, we know the concentration of these gases, and then you're able to kind of expose your multi-gas to those gases and say, all right, let's make sure these levels are reading what we expect it to read.
Claire, I'll go ahead and ask you something. That when you talked at the beginning there about the occupants of the island, I don't think you mentioned bears.
Yeah.
And there was a little thing that occurred at the beginning of the trip, if I remember right.
Yes, I didn't see the bear, but others saw a bear. So Cruise Off Island and down in that area kind of has one of the highest concentrations of brown bears, which is not a good thing to run into. I'm aware, however, they are my favorite animal, so I was not hoping for it to happen, but it was kind of exciting. But we did see a bear, so we had to kind of move our spot where we were trying to measure because there was a bear that was coming closer to us, and I think maybe it had some sort of kill on the other side of us, so not in a great spot to be, so we had to move away, but we didn't run into any other bears after that. However, I did capture one bear on my trail cameras, which only one, but I was very excited because they are my favorite. So,
I had a question. Since Edgecumbe seems to be an anomaly as far as volcanoes, are there other structures like that in Southeast Alaska?
it's a great question. Yes, Edgecumbe is an anomaly. Let me bring us back to one of our first slides where you can see all the different volcanoes. Almost there. Okay, so here we go. That's a great point. So you can see that most of our volcanoes in Alaska are along the Aleutians. And right below the Aleutians, where you see that kind of really dark blue line almost down below, that denotes that there's this big subduction zone where you have the oceanic crust going down beneath your continental crust. And when you have oceanic crust going beneath the continental crust, as it gets closer down to the hot core of the Earth, right, you get some melting happening of that crust. and then that comes up, and then you get a nice volcano. So it makes sense that we have volcanoes all along the Aleutians because we have that subduction zone. However, in Southeast Alaska, you're right, we don't have a subduction zone. We've got two plates moving past each other like this, and usually we don't get volcanoes there. So it's kind of weird that we have Edgecumbe there, and we're still kind of, the scientific community is still trying to figure out why is it really there in the first place. There are some theories, but it's still a weird one. But you can see down in Southeast, there are a couple other little triangles there, southeast of Edgecumbe itself, the names of which are not coming to me right now. But we do have some other volcanic features down here. However, they have not been showing any unrest or deformation or seismicity.
All right, I have a question on my side of the room here.
And just to add to that, if you go to the Alaska Volcano Observatory's website, which is this one right here, you can actually, this is the main page that pulls up. It's really user-friendly. You can just click on the triangle, and it will tell you what that volcano is. So I encourage you guys, if you're interested in these kind of anomalous, strange volcanoes down here, to go to that site and click on them, and you'll get a little more information.
Yeah, hi Claire, great presentation. I was wondering, when you showed this map of temperature anomalies, how can you make sure it is not something related to a surface process or something like that? Because it seems the island is pretty well covered in vegetation, while the dome seems to be a bit more naked. Yeah, how do you analyze all this?
Yeah, so that's a good question. There are a few things that we do to make sure that the temperature anomalies that we're seeing are actually from a volcanic process, or that they're truly changes. Some things that would affect the temperatures on an island would be, or on a ground surface, the time of year, right? It's colder in the winter, warmer in the summer. If there's snow on the ground, that's gonna affect things. As well as you can have daily variation in your temperature trends, right? It's gonna be colder at night when the sun's not out, and be warmer when you have the sun there. And we filter those out. So we apply a daily and a seasonal filter to get rid of any trends that correspond to daily changes or seasonal changes. However, really key point is another thing that affects this type of temperature, which in fact is not a true temperature, it's what we call brightness temperature. It's a different metric of measuring the radiation that we're getting coming off of the ground source. And that brightness temperature, that radiation, can be affected by changes in the source of that radiation. So how good of an emitter is it? How good is it at putting off that radiative heat that we're then collecting the data for at the satellite? And some things that change that are different plant biologic activities. So if your plant is really unhealthy, or if it's dying, right, it's gonna emit that heat differently, that radiation differently than if it were super healthy. Or if you have a change in your plant type, that would change that as well. And so that's another thing that I've been analyzing, is looking at just that property is called the emissivity, how well of an emitter the ground source is, and tracking, using the same way of tracking the changes in the emissivity, how well of emitters that surface is. And so we can see, is that property changing in the same way that our temperature trends are changing? And then we'd say it's probably just due to the fact that the ground cover is changing. But we don't actually see that. We see a pretty consistent. The efficiency of these emitters, if you will, is not really changing over time. So that helps us try to determine if it is just from those other biologic changes.
All right, any other questions? One on the other side there.
Thank you. South of the map where Edgecumbe is the anomaly, between that point and then the start of the Cascadia subduction zone off the west side there of Vancouver Island, are there any other, I guess, anomaly volcanoes similar to? Or is that as far south as you've really looked at this point?
That's a great question. And often I have bias, right? When you're looking at Alaska, I'm like, it's Alaska.
Right.
And you forget that Alaska continues, or the landmass continues. So there are, right, you've got the Cascades, and if you're looking up through Washington, those volcanoes do continue north into Canada. And there are a few sort of anomaly-looking volcanoes. However, I'm not 100% sure, but I do believe as you start to go southeast of this area, they kind of jump to the other side of the mountain range there. That's right, yeah. Which kind of makes an interesting play. So right now we're kind of along a large fault system is where Edgecumbe sort of falls there, that those faults that are moving past each other like this. And those other volcanoes south of that seem to be further away from that fault system, and I believe they may be far south enough that we might be getting towards that subduction zone, but don't quote me on that because I can't think of the map in my head.
Thank you.
Yep.
Is it coming in? There we go. I have some questions on Zoom and Facebook. So question from Harold on Facebook. Great presentation. Could the quake activity be related to seawater migrating into the chambers?
So that's a good question, but likely no. So oftentimes when we think of a magma chamber or a reservoir, sometimes our first thought is that there's like this empty void space where you would fill up with magma or there wouldn't be magma there. But in fact, it's not an empty void space. It's full of magma or full of this kind of, it's called a magma mush sometimes. And so there's not really an empty void space for any seawater to be moving into. And you would also need a lot of, one thing that we would see, right, if we have water interacting with hot magma or water chambers, that's going to create a lot of steam. So you'd see a lot of, maybe you would see some steam eruptions, maybe you see some steam emissions, and we don't see any steam emissions. So yeah, one thing we want to keep in mind there too is that we don't have a void space where water would be able to really enter in, and then we're not seeing any steam, so we're not seeing evidence of water interacting with hot magma.
All right, a couple more from Harold. Has the magma chamber moved in relation to the craters like Hawaiian volcanoes? The magma chamber is stable and the plate moves over the hotspot.
That's a great question. So in this area, we don't have hotspot volcanism happening. We don't believe that we do here. We have, again, that subduction zone, and then where Edgecumbe is, so there's two plates moving past each other. And what we believe is going on beneath the surface is that you've got one idea, right, is if you've got these plates interacting on the surface or sliding past each other, but it's not necessarily, as you go deeper, down beneath the surface, they're not necessarily plate walls that are straight up and down. Perhaps they're dipping slightly. And one idea is kind of as that dips, you're reaching a zone where you're able to get some melting happening as that fault kind of, if it dips below slightly, then your fault zone becomes underneath Edgecumbe itself, because in fact that fault zone on the surface is a little bit west of Edgecumbe. So you think that that's dipping, and then we're getting some melting along that fault, and that's what's producing our volcano. And so it looks like that's been a consistent location. Of course, on Cruzoff Island itself, here, we can see there's a number of different volcanic features. I don't know where my mouse is, right here. So Edgecumbe, you've got Crater Ridge, and then we've got all these little cones. Sorry, this sign is blocking some of them, but smaller cones. And so those are different areas where we're getting magma, rising to the surface through these different vents. But that chamber seems to be consistently in one spot, and we don't have hotspot volcanism here like we do in Hawaii.
All right, one more from Harold. Regarding the mantle, is the chemistry of the mantle consistent across the planet? Is this how you determine if the gases are from the mantle or organic?
Yeah, so yes, we can look at the chemistry of the mantle. Mainly, one of the things we like to look at is those helium isotopes to tell us about our mantle source. So those are usually very consistent. The ratio of our helium-3 to our helium-4 coming from the mantle is consistent. You can see some changes in the composition of your gases that you would expect dependent on the setting of your volcano. So if you've got subduction zone volcano, if you've got those hotspot volcanoes, which is not what we have here. If you've got someplace like Edgecumbe, you're going to see slightly different changes in the composition that you would expect for your gases. But yeah, here at Edgecumbe, since we don't see any of those gases, we're definitely not seeing that. But yes, the mantle is pretty consistent, so that's a really good source to tell if the gases we're seeing are from the volcano or not. But we do see slight changes in those compositions depending on our volcanic tectonic setting.
All right, thank you. This next one is not from Harold. It is from Corey on Zoom. Are you planning any return trips, and what other monitoring systems are planned?
It's a great question. I would love to. I love Sitka, so that would be great to go back. And it's a really cool place. There's a lot of great stuff to explore. Me personally, I'm not planning any return trips, but I do know that the Alaska Volcano Observatory is planning more trips back there. So the trip I went on in August, the second trip, was with the Alaska Volcano Observatory, where I was doing this gas work, but other folks at the Volcano Observatory were doing some geology work, so looking for outcrops, looking to check where, to find out more about the rocks on the island. And then we had our geophysical crew that was installing some additional monitoring networks on the volcano. So we now have 4 monitoring stations. One sits here, or the Alaska Volcano Observatory now has these 4 monitoring stations. One sits here on Crater Ridge, one sits here south of Edgecumbe, then there's one east, and then there's one west. And these all have seismometers in them too, so that we can detect earthquakes and locate them better and figure out where they are on Edgecumbe. This allows us to be able to detect lower magnitude earthquakes, so a lot smaller earthquakes, and locate them better to see, are they changing their position, their magnitude. So there is that monitoring equipment, and then I do know that, yeah, there's more work planned that the Alaska Volcano Observatory will be doing, but sadly me, I don't have plans right now, but we'll see.
All right, question from Roman on Zoom. How does snow cover affect your regional temperature fields?
Yeah, so that's a really great point. Snow cover is really going to affect that temperature, and that's why we do filter out any of those daily or seasonal trends that I was talking about before. So if we see a trend that looks like, oh, it starts to get colder in the winter and then it's getting warmer in the summer, we're able to kind of filter those out to get at any more subtle temperature changes that are kind of hidden below that deeper signature. So we filter it out.
All right, just a couple more online questions from Whitney on Zoom. Did you discern the vertical change between isostatic rebound and volcanic deformation? Sounds like she knows what she's talking about.
She knows more about it than I do. So yeah, I didn't perform that one myself. Again, that's Ronnie Grappentine and his team. And I'm not quite sure if he did, but I would assume that yes, he takes that into account. But Ronnie Grappentine is at the Geophysical Institute, and I'm sure, I know his email's online, I'm sure he'd be happy to take questions about that, but I'm not quite sure if they, take that into account, but I would assume that they do.
All right, and from EJ on Zoom, how does Goddard Hot Springs play a part of Mount Edgecumbe?
It's a great question. So Goddard Hot Springs is located just south of this map. It's a little bit further down here, if you can see where my cursor is. These are these really cool hot springs that I have not had a chance to visit, but they sound awesome. So these nice hot springs down here, and it actually doesn't look like Goddard Hot Springs is that connected with Mount Edgecumbe specifically, or not, from the volcano itself, but it looks like there is some faulting that is in this further southeast region that is allowing water to kind of circulate, get hot, come back up. And we don't think that it's actually related. We haven't seen any changes at Goddard Hot Springs that we know of. There haven't been any local reports of anything different happening there, any changes in temperature, and folks are out there quite often from the Sitka area. So no changes have been happening, and we do think that those systems are relatively separate from each other. I think, does that answer the question? I hope so. Let me know if that doesn't.
Any last questions from the in the audience here? Oh, we got one. It's on your side. I'll take it.
Hi. I just have a question about the gas section. You were talking about the bubbles that you found in the pond and that there could be potential biological activity that could be causing those bubbles. Do you have any idea as to what kind of biological activity that could be?
Yeah, so this is, that rabbit hole I've started to go down a little bit. But you can get carbon dioxide, and you can get, and other gases too. It's mostly nitrogen, again, that we're sampling here, through different processes with plants, through plant decay, through just respiration, and mostly plant decay. You're going to get some, Mostly plant decay. I'm not going to go this too far because I haven't gone down that rabbit hole super far. But those plant activities, you can have microbial activity too that can be producing these gases. And so one idea is maybe there's a way where those gases are being produced, and there could be some area kind of maybe below that pond where there's a little bit of a void space. Maybe they're able to build up, and then they're only released when you have enough pressure from those tides coming in that's allowing that to be released. So there could be some area where it's able to build up and store. It usually isn't something that happens. You're usually not seeing persistent bubbling like that. So my thought would be there's some way it's not able to be released. It builds up, tides come in, allow that pressure to be released. Thank you.
Okay, I think we will call an end to the questions there. Maybe one last thing, Claire, you could share before we start to wind down here is there was some international interest, the makeup of the team.
Yeah, that was great. We had some colleagues, as I mentioned before, from Italy and Spain come. Oh, I can pull back, but that was Carlo Cardellini from Italy and David Benavente from Spain. And Carlo Cardellini is he's a gas expert. He works on these carbon dioxide fluxes. I actually had the privilege of going to work with him in Italy to learn how that accumulation chamber works and to learn how that field work is done. And so he's an expert there. And then David Benavente is also a gas expert and a radon expert too, but we didn't get to really tap into his radon expertise in this, unfortunately, because we couldn't sample radon very well while we were there. But yeah, that was very exciting to be able to bring folks from those international institutions as well as people from UAF, and then to be able to work with the Alaska Volcano Observatory and some folks from USGS at large too, which was kind of a treat to get so many different perspectives.
All right, let's hear it for Claire. Good, great.